We're going to be going over DRBD along with LINSTOR, which is our software-defined storage solution. And then later on later the morning or afternoon, depending on where you're located, we'll be going over LINBIT SDS's integration into CloudStack. It looks like the attendees have topped off, so I don't know if we want to get started, Phil.
Okay, let's get started. Then, so welcome to the first session today. I will talk mainly about DRBD, and then please follow on to the second session a little later. So I'm your host, Philipp Reisner. I'm one of the founders and CEO of LINBIT, and still a lot involved with one of the parts of our software stack, and that's DRBD. So the whole software stack, that is LINBIT SDS. And let me begin with an overview. So let's find out when LINBIT SDS is a good fit, why you want to use it, and what it is from a very high level of abstraction. So when is it a good fit? It's a good fit when you need persistent volumes for containers, or let's call them persistent volumes for virtualization. And this is exactly where we are. It can provide persistent volumes for your CloudStack cloud. And not only for that, also for a few other technologies that might compete with CloudStack. It is a very good fit if you need some performance from your virtualized storage. So it is a good fit for anything doing transaction processing, like structured databases, Oracle, Postgres, MariaDB come to mind. And it's also a very good fit for message queuing systems. Actually, one of our bigger customers embeds DRBD in their HA version of the message queuing system. Also for different kind of database, what we see in analytic processing, what we do is a very good fit. Because for these kinds of workloads, you need high read performance while doing all the queries against your data cubes. And this works very well when you have the storage co-located with the database engines. So it was really beating all the competitors in the space for the DB2 warehouse workload. So why is LINBIT SDS so fast compared to the other players in the field? So the data path, we built that completely out of in-kernel components. So that allows us to do some tricks with reducing the number of necessary context switches, and in general, save on CPU and memory resources. Another way how you can make it faster is when you co-locate storage and your actual workload, because that gives you better read performance. But let's talk about that a little later. Another aspect is that we lay out at volume allocation time. So that means in the moment we create a virtual volume, LINSTOR decides on which nodes replicas of this virtual volume go. And when it is time to process an IO request, all that is preset and is no longer doesn't take any time in processing that IO request. LINBIT SDS is built from existing components. So we don't want to reinvent the wheel because there is so many reusable components in open source software. We should use that. And that not only makes life easier for us, but it also makes life easier for you when you try to operate this software-defined storage. Because your operation team might have knowledge about some of these building blocks and they can continue to use this building block, their knowledge about these building blocks. So the whole SDS is not a proprietary black box put in front of your operations team, but it is something composed of components they might already know. So we are building it on the shoulders of giants. And the whole system is very well suited to be used in a hyper-converged way. So this is actually the way what we recommend. And the reason for that is that DRBD and LINSTOR, the components of LINBIT SDS, they have a very small footprint on CPU and memory consumption. And it even helps your performance if the whole system can co-locate workload and storage replicas on the same machines. And I want to remind you that this is in strong contrast to some other SDS solutions out there, which might have a hefty CPU footprint and where you need to plan complete cores dedicated to the SDS. So that's definitely not the case with what we are doing. We will consume just a very tiny fraction of a single core of your many core server. And what is it doing? So it manages the storage aspects of a number of machines, and that can be any number between 3 and thousands of nodes. So currently the biggest cluster that we know has about 630 nodes. And from the performance data we see from that cluster, we are pretty confident that it also scales to 1,000 or even more nodes. And it manages the storage in storage devices, maybe or probably built into these nodes. And you can arrange that in pools, maybe multiple pools, like reflecting the tiers of your storage. So maybe an SSD pool, maybe an hot HDD pool. And LINBIT SDS is about persistent volumes. And we live in a world where we always assume that single nodes might fail or that storage devices within nodes might fail. So we have to do replication. And we support two-way replication. So I mean with that you have two replicas of your persistence data, three-way replication, 4, 5, 6. I don't see six-way replication that often in the market, but the software offers it. So usually you would do 2 replicas or maybe 3 replicas, or maybe 3 replicas is in one data center plus some additional replicas in another data center or in another file compartment. Replication can be synchronous or asynchronous, and it can also be mixed. So let's say you have 2 synchronous replicas within a DC and then another third replica in another data center. Supports consistency groups and quorum. Let's come to that later. It can choose between networks and paths on your network, and it can do that in an automated fashion for you. And all of it can be part of your business continuity plan since it replicates the important data on the fly. So this was like the very high level flyover. And now for this first session, I want to continue to go a little deeper into one of our core building parts, and that's DRBD. So DRBD is a driver for the Linux kernel. And when you view it from a very abstract point of view, it is like a RAID 1 between a local block device and an initiator. And the initiator is connected to a target, and behind the target is a second replica of your data. And so these are two machines. But this is just, let's say, a mind model. It is implemented as a monolithic driver on Linux. And after loading the driver and after configuring it, it will offer you device files. So let's say def DRBD 0. And you have that on two machines. In the moment you open this device file for read-write, it promotes to primary and becomes accessible to you. In the moment one guy is primary, the direction of replication is determined from that. If you want to move your application, that's quite easy. You stop your application, unmount the file system. With that, it demotes into the secondary role. A moment later, you mount your file system here, start your application. With mounting, it promoted to primary, direction of replication is reversed, and your application is running on the other node. DRBD can work with multiple volumes in a single resource. Yeah, we call it volume groups. And well, in DRBD, we call it multiple volumes. And the industry terms for that is consistency groups. So that means a DRBD resource might have 2 volumes in it. And let's say the backing devices, the actual storage media is pretty different. Let's say one of these two is very fast. Let's say an NVMe drive. And the other one could be something completely different. Let's say a RAID 6 of rotating hard disks. And then we have an application that is using both together. Let's say it's a Oracle database writing its intent logs onto the fast volume, and the table space is allocated on the huge and cheap volume. If we replicate such a thing, it is easy to understand that we must replicate them in a, let's say, lockstep fashion, right? No writes might overtake each other when they're replicated to the secondary. Otherwise, the database wouldn't be able to recover in case of a failover. So that's supported by DRBD. DRBD would support up to 60,000 volumes in a single resource, but nobody needs that. So usually it's 2. When talking about scalability, DRBD is a multi-node technology. So each DRBD resource might be replicated to a single secondary, but also to 2, 3, or more. Each replication link might be synchronous, or it might be asynchronous replication that can be switched at runtime. And with having this multi-node capability, it also becomes possible to have nodes that don't have a local backing storage for the volumes. So in DRBD speak, we call them diskless nodes. So this illustrates a 3-node setup where only 2 have backing storage, but the resource is primary here. So that means it is in use here. So that means the file system is mounted, the file systems are mounted, the application is running, although there is no backing storage on this node itself. So it can think of it as, it is just as having here an iSCSI initiator, software iSCSI initiator, connected to two iSCSI targets. And that's different from iSCSI. In iSCSI, you can connect it only to one target. And all the writes go to both concurrently. And if there's a read, DRBD does a load balancing and sends one read here and one read there. And if something fails here, let's say this secondary fails, and it just got a read request, and it cannot send back the answer to this read request because it crashed, then this primary will figure that out and retry the read request here and then deliver the data of the read request to the application on top of it. So the application is shielded from any kind of failure as long as possible. So being it storage device failures or node failures or network failures. If a crashed node comes back after some time, is automatically reintegrated into this DRBD cluster. And the two secondaries will figure out that the crashed guy missed a few writes, so it gets a resync. All the blocks that were touched in the meantime get copied over. And when that process is finished, its disk state goes to up to date and it becomes available for IOs from the primary. So this is how DRBD works as its core. And so it got a number of features over the years since we are developing this. So DRBD is roughly in development since 20 years now. So it got a number of features. So maybe I want to note the quorum feature. So with quorum, this old problem of replication has a solution. So the problem that's inherent to all replication systems is called split brain. So a single node can never know, in the case it loses the connection to its peer, it doesn't know by itself, is just a network interrupted, and is the peer still alive or is the peer dead? And in the moment you turn on quorum, you can avoid all the split brain problems. So this is implemented in DRBD. It requires that you have 3 nodes in a DRBD resource, but LINSTOR will take care of that. DRBD can handle many resources on a single server, so up to thousands, and it supports a dual primary mode, which is intended to do live migrations of VMs. So it's not intended for production use with a shared disk file system on top of it. So don't think into that direction. And yeah, then what have we done recently? Recently, we did a lot of optimizations for persistent memory and NVDIMMs. So it's especially if you put the DRBD's metadata on one of these new storage or new types of storage media, it will take advantage of the new capabilities. So persistent memory and non-volatile DIMMs are a new way of persistently storing data. You can put them into your servers where you have the regular DRAMs. And yeah, then they're presented by the Linux kernel as block devices. And they have a special new property. You can access the storage on these block devices on byte granularity. And that's a new feature that's not possible with SSDs or hard disks. And DRBD takes advantage of that. in case its metadata is located on one of those devices. We are always, let's say, driven by our customers to improve performance. So as you know, SSD and NVMe performance raises like every year. And we need to follow that so that the software is not becoming the main bottleneck in the stack. Yeah, so that you find in the DRBD 9.1 branch that has the latest performance optimizations. And yeah, maybe a side note, even we have a Windows port of DRBD going on, and that is literally weeks out of reaching the first production release. Okay, so that's the content I wanted to talk about in this first session. More follows in the next session, and now I give you a chance to write some questions in the Q&A area. And if there are no questions coming up, we can switch to a view VMs and do a small demo of the DRBD part. Okay. No questions at this point, so.
Yeah, if we get additional questions, we can answer them as you go along. Phil, I can answer in the Q&A for you.
Okay. Then I switch my screen sharing. Let's see how I do that. Here. Okay, and
looks like we did get a question, Phil. Are there any differences between DRBD and Veritas InfoScale series of solutions, like the volume replicator?
Okay, the thing is that I probably don't know enough about the Veritas product. My background from being in the industry is that the two products can replace each other, but I don't know enough details about Veritas to give a reliable answer. Okay, then I start with a small demo here. I guess you can now see my screen share here of 4 black windows, right? So let's see. Okay, so when I use DRBD by hand, I need to create or make available the block devices I want to use for DRBD. So here for my demonstration, I have LVM volume group called Scratch. Yes, and I just created a logic volume called R0 on these 3 machines. And I think I have here a configuration file for DRBD prepared. Yes. And yeah, so what is in here? So it is a keyword, the name of the resource, a few options. Let's look at that a bit later. I give it here a few host names. So on D1 and D1, that's the name of this virtual machine. So it's called D1 in the domain test. It should use this node ID, and that's the IP address and port it should bind to. Similar for D2, D3, D4. So it's a resource with replicates onto 4 machines. And what else do we have here? We have a volume, device -0, so it will show up as def DRBD 0. It should use the backing device, def scratch R0. This is what I just created with LVM. Metadisk is internal, so it's metadata go at the end of this backing device. And then some disk properties. This is about the resync. Then I have here an exception on the node 2. It should be a diskless. And yeah, D3, D4, and then a connection mesh. So each should connect to everyone else. And we're going to use protocol A, the asynchronous protocol, and some more configuration details. And then the first step is that I need to create the metadata. And I need to do that on 3 nodes. Oh, okay, yeah. The configuration says there is no backing device. And then the next step is that I activate the DRBD resource. And now we can query it for status. Okay. So what happens so often in demonstrations? Something goes wrong, right? But let's find out what it is. So
Bill, do you think you could
says,
increase? Do you think you could increase your font just one size, maybe?
okay, of course. Sorry. Is it now better
There we
readable?
go. I think so. I can see it fine on mine now. Yes.
Okay. Okay. So, and after activating it for the first time, it considers that the replica set is completely inconsistent. And now I need to tell it which data set it should consider as the real data. So I can do that in this way. Yeah. And so now it's up to date here, and it's also up to date on this node. And they have an issue connecting to D2. So I think maybe it's a leftover that I have a configuration mistake in here. But before going into that, let me show you how I would use that. Okay. So now what happened here is I made it secondary again. So this is this explicit promotion. I need to initialize the whole thing. Then I created a file system. And now we can mount the file system, def DRBD0, MNT1, for example. And in the moment we write something there, yeah, it is replicated in the moment this machine writes it out, but we cannot mount it at the same time on the other machine. that will fail in a second. And the reason is the dual primary mode is not enabled. And that is my intention, and that should be that way. Because a regular file system like ext4 will not tolerate to be mounted concurrently from multiple hosts. So in order to look at the content, we need to unmount it here first, mount it on the target machine, which works now. And now we see the file I created. Here it is. Okay, so this is the very basic things DRBD does. And there is a lot behind the scenes, right? So there's a lot like when everything crashes, how does it find out in which way to resync, in which direction, which blocks to resync. So it does efficient resyncing, even if the storage is huge, right? If the volume would be hundreds of terabytes in size, and the two peers lose connection for only for a few minutes, then it would resync that in an efficient way. So only what was touched in the meantime. And yeah, there are lots of details and bells and whistles, and something we can work on for such a long time. But I don't want to overload you with all that at this point. If there are no more questions.
Looks like we've got a few.
Oh, okay. Then
so,
I stop here and let's have a look at the questions, right?
Yeah, perhaps just answer them live. I think that'll be the solution.
Yes. So, yeah, a few questions. Perfect. Okay, then I start with the first one. Could you tell us about any QoS controls you have and for dealing with noisy neighbor scenarios? Yeah, so we are a building block in Linux. And in Linux, there we have control groups. And with Linux control groups, we can limit the I/O operations per second and the data throughput a certain volume can do. And all these QoS controls are available to DRBD devices as to other devices. And if you do that by hand, it's pretty complicated, but we have integrated that with LINSTOR, and we will talk about in the next session. Okay, then I pick up the next question from Piotr. Hello, if you have 3 nodes, a volume with 2 replicas, node 1, node 2, node 2 will crash, second replica is picked up by node 3.
So I think similar to the constraints that you can put in LINSTOR, where it says you always have to have, or the policies, excuse me, that say you always need 2 copies.
Yes.
So I think
right.
the answer is yes if you're yes if you're using LINSTOR and DRBD together, I believe, correct?
Yes, that's the answer. So LINSTOR does all that behind the scenes as you would expect it. So exactly as you are asking it. Okay, then let's go to the next one. Can you show us the DRBD configuration files? So I guess that was related to the live demonstration I did. And I think I showed it. So let me go to the next one. How can we back up a DRBD disk? Yes. So again, we will talk about in the LINSTOR session. That's the next one. LINSTOR just recently got the capability to backup volumes into S3 storage, and it can do full backups and incremental backups. And for incrementals, it relies on the CFS snapshot send receive feature and on LVM thin. There's also a way to back up snapshot differences in an efficient way. So yes, backup topic is covered by LINSTOR. Okay, then I go to the next question. This is like my favorite one. What are the differences between LINBIT and Ceph? Yeah, so what we do with LINBIT SDS is it is all on block device level. So it's really optimized to deliver good performance as a block device. And that is comparable to Ceph Rados. Ceph Rados or Rados also gives you a block device. The huge difference is that Ceph is an object storage in the background. And that delivers a lower level of performance if you want to use it for pure block storage devices. And Ceph has a much higher footprint when it comes to CPU and memory consumption. So when I put these things together, the difference is LINBIT is faster and uses less CPU and less memory. On the other hand, Ceph is more versatile. Ceph can also do S3 block storage. It also has CephFS. It can also do erasure coding. So it has other features which are out of the scope of LINBIT SDS. LINBIT SDS is only block storage. So in block storage, that is like a virtual SSD or virtual HDD. Then I go to the next question. Hi Phil, since version 8.4, you have a very slow by default performance. Are there any recommendations for adjusting the performance? Well, performance is a never ending topic. It doesn't fit into answering here a question. There are many ways at looking at performance. You know, are you going for throughput? Are you going for IOPS? What are the constraints? What are the performance of the backing devices, of the network? DRBD can be tuned to the workload. So you can tune this activity log. And we have certain things, how DRBD performs while resync operations is ongoing. And we have upcoming, so that's still in the development pipeline, a few optimizations where we are going to reduce the latency by eliminating a few context switches within the kernel.
So I think to expand on that a little bit, by default, we do choose slower options, but that's just because we don't know the hardware that we're installing on. So we go with the safe bet. There is a pretty extensive section in the DRBD users guide, which can be found on linbit.com, that goes over performance tuning. I believe we also have a couple videos on YouTube. And I know if performance is something you're after, I believe you want to go with DRBD 9.1, as there is an extensive overhaul of how DRBD manages its read and writes. So I think if you want speed, go with 9.1.
Right. And there are many ways how you would say, let's say, optimize your hardware to achieve the highest possible performance. And yeah, regarding performance, we also have this blog article, the 12 million IOPS world record, something. So you can find that on the blog. We will paste the link into the chat. Okay, I think we made our way through the questions.